Okay, sorry again. So we will try to speed up to avoid the next shortage of connection. Very sorry for that. The first will be a very short introduction of our company. After that, I will give you insight on the, let's say, LNG market, starting from the upstream facilities, downstream facilities, and in the middle, the vessels. And after that, Jesus will follow up with let's say more specific description, more technical, based on the assets, on the downstream assets.
Yes, so only one thing, because in the presentation with these interruptions we didn't say the name of the presentation. That is LNG Global Trade, from the LNG terminal to the truck. That is used normally for supply gas to any kind of user, either vessels or industrial or domestic consumers.
Okay, very short overview on our company. Reganos has a specificity to be both an LSO, is to say an LNG terminal system operator. Sorry for the vocabulary. It is a European vocabulary, and also a TSO, transmission system operator, as the no te preocupes. Okay, so okay, sorry for that. Okay, so we are quite a small transmission system operator with only 180 kilometers of gas pipeline, 130, so it's very high pressure, 80 bars. The LNG terminal is quite a common one, 3.6 BCM per year, including a small one. And in terms of storage, it is in the middle range in Europe, but with 300,000 cubic meter of LNG, and a capacity to load 10,000 tanks per year. Okay, the three rules, the golden rules for Reganosa is the safety. Clearly, we are, let's say, dealing with inflammable products. So it is the first rule, the golden rule. After that, the flexibility, and we will explain you why. And finally, the efficiency, because we're a small company, but with, let's say, the ambition to be present in all the business we are covering. We are a member of ENSOG. ENSOG is very relevant association at the European level, because ENSOG is in charge of developing all the network code enforcing Europe, covering tarification, access, capacity management, and so on and so on. We are also a member of GIE, which is, let's say, the European Association for all the owner of infrastructure. We are also a member of SEDIGAS, the Spanish Gas Association, as well as GasNam, which is, let's say, a Spanish association focused on the gas as fuel, either for road usage or for marine usage. Okay, so the needs for LNG is basically coming from the growing distance between the supply point, the production point, and where the demand is located. And this distance is growing because of three, let's say, simultaneous factors. The first one is the decline in production in Europe, especially in the North Sea. North Sea gas resources were shared by UK, Netherlands, and Norway, and the level of these resources is declining every year. Okay, the second impact is the increase in demand in Asia, except maybe Japan, because Japan, after a snapshot in terms of LNG consumption, is now coming back to the normal track. This peak of demand was due to the Fukushima disaster, and it is restarting the nuclear plant one after the other, so that the consumption is mainly driven by China and South Korea in this area. And as a third point, the new discoveries coming from the shale gas, especially in US, and also in Australia. And Middle East is not that new. Is not that a newcomer in the market, because let's say especially Qatar, when we are thinking about Middle East, we are talking about Qatar, obviously. Qatar is now on track since 10 years, more or less. So what I present you is data about the reserve of gas with the evolution along the 20 past years. So the first thing you can see is that on a different way, or the different trend than the crude oil trend, the reserves are growing very quickly, so that the estimated year of reserve is also growing. And you can also notice that the reserves are concentrated in the Middle East, so that there is clearly a need for transporting this gas produced in Middle East, but not consuming in Middle East. Okay, so the supply chain can be presented that way. There is first the extraction, the production, the liquefaction facility. So to have an idea, we consider that roughly 40% of all the gas traded worldwide is traded under the LNG form and against the pipeline. Okay, so in the case of the supply chain for LNG, we come to the liquefaction train. After that, we enter into the shipping, the transportation of the LNG. Once liquefied, we finished the journey at the receiving terminal, for example, Reganosa, here illustrated. After that, we proceed to the regasification and we send the gas in the natural gas transmission system. Let's start with the liquefaction facilities. I will go shortly through this presentation because it is not the topic of today to know exactly how it is working, but it is also always interesting to understand the complexity of the process and why it is so expensive to liquefy the natural gas. Okay, the idea is to use a typical Joule-Thomson depressurization that will lead to a cool down of the natural gas. So what there is first a propane loop which is compressed and depressed so that the temperature is decreasing. So if we consider a compressed C-trace, it is exchanged with the natural gas so that there is a first cooling down of the feed gas, and so on with different stages of pressure. Okay. In the middle, there is a very important loop, which is a mixed refrigerant. The process I present to you today is the most employed worldwide to ensure the cool down of the natural gas. So this mixed refrigerant is, let's say, a compound of light ends, especially ethane and ethylene. This ethane is cooled down by the propane, and on a cascade, this mixed refrigerant is used to cool down the feed gas. Okay, so once the mixed refrigerant at a low temperature, there is here a flash, so that the heavy ends with the less capacity of cool down are going at, let's say, the mid-level of this thermal exchanger, while the light ends are routed on the top of the exchanger, so that when the feed is climbing along this final exchanger, the temperature is decreasing. Okay, and the final cool down, because the LNG is obviously subcooled to avoid excessive vaporization during the trip aboard the vessel, there is a final depressurization that ensures the subcooling of the LNG. The LNG is then routed to the tank, ready to be shipped. A rapid overview about the distribution of the liquefaction facility around the world. As you can see, and it also complement of the reserve I present you before, you can see that the liquefaction facility are spread worldwide, which is quite different from the crude oil, so that there is no cartel of producer of LNG as can be the OPEP, as an example. Okay, so in terms of market, it has a huge impact because there is no clear control of the quantity and of the prices. It is, let's say, a much more liberalized market than the crude oil market on this aspect. Okay, so basically few facilities in South America, but these facilities are mainly dedicated to the European market. And the coming ones will be located in the Mexico Gulf. I will tell you a little bit about these facilities, which is the new, let's say, the new trend, one of the very new trend. The figures you can see in bracket are referring to the order of startups. So you can see that the oldest one is Kenai, Alaska, an energy plant initially historically dedicated to the Asian market, obviously due to the distance. Now, the big producers are located in Qatar, mainly here. There is a huge reserve of gas. In North Africa, the situation is a little bit different. Because of the huge domestic consumption, there is less gas available for the export market. So that, for example, the two terminals in Egypt are now shut down. Libya, obviously for geopolitical reasons, is not producing anymore. Active producer is Nigeria. Nigeria is one of the main producer and main supplier for Spain. And in, let's say, in remote Asia, new producers are coming from Australia, which is really the big player. I will show you after that Australia is expected to be a larger producer than Qatar in terms of LNG on an annual basis. And also the traditional producer in Indonesia and in Brunei. There is an interesting phenomena, for example, in Indonesia, that export terminal, because of the complete depletion of the gas field, are converting into an importing terminal. It is a phenomena which is exactly the reverse phenomena that it is occurring in the regasification plant in US. A short view on the different qualities, because as I just showed you, there is different technologies. I present you before the mixed refrigerant, but there is a large range of technologies. There is also a large range of different fields, so that the final quality of the LNG is not the same. So basically, here the consideration are the same than from the crude oil. There is large range of crude oil qualities, it's the same. There is a large range, of LNG qualities, starting, let's say, from the lighter, basically Indonesia, but Trinidad also, which is more active right now, is well known to be very light LNG, going to extreme value as Libya, which is not producing anymore, but we can also mention the Oman LNG. What is interesting talking about technology is that if you have a look on Algeria, all the gas is coming from the same gas system, basically from the same field, but there is 3 different facilities that ensure the liquefaction of the Algerian gas. And as you can see, the same field with different technology, because the year of the startup, basically, are very different, and it is quite interesting to see a quite large range of quality coming from the same field, just because of the technology employed for the liquefaction process. Now, if you have a look on the quantity, what is very relevant to notice is that Australia is a newcomer. You can see here the capacity in 2014 and here the capacity in 2020. So the newcomers are Australia and US starting almost from zero and growing to, let's say, very important value, including close to Qatar capacity. So so US and Australia are game changers. They are reverting absolutely the gas market and changing the way the gas is priced worldwide. What is also interesting to notice is that these facilities are almost used at full rate. You can say me that in US it is not the case, okay, but US we are referring to the Alaska plant, and this plant is working on the stop and go mode. So it is not referring to the new coming plant. This one started up in the middle of the year, so that the rate of use is obviously changed. In Indonesia, Indonesia is suffering the depression of the gas field, so that it impacts negatively the send out of this liquefaction train. And finally, you can see that Algeria is also facing a lack of feed gas, as well as Egypt, mentioned before, and Angola suffered problems during the startup, so that we expect to come in line in 2016. And basically, that's all. Let's say that apart from this liquefaction train, the existing ones are running at full rate. Now, speaking about CapEx, what is very interesting is that as a consequence of the growing number of LNG liquefaction train, we can logically expect more competitive prices, but it is not the case. There is clearly a bubble in terms of cost. So what you can see here are the greenfield. So greenfield, we are referring to new LNG plants starting from scratch. Brownfield, basically what we're referring to, brownfield is referring to existing import LNG terminal, is to say regasification plant, that are converted in export terminal, which is, let's say, a good idea. You can see that it allows the promoter a huge discount, basically because important investments are yet done. After me, Jesus will explain you how important are this investment, and you can see that if a jetty is yet built or LNG tank are yet built, it allows you to save a lot of money, sorry, compared to a pure greenfield project. What you can also see on this slide, which is interesting, is the emergence of the floating technology. It is quite surprising because when you see what is a liquefaction train in Qatar, for example, thinking about putting all this stuff, all these assets aboard the vessel is difficult to imagine. But I will show you an example in the next slide of what can be done. Basically, the floating technology is appearing as a consequence of the very high labor cost in Australia. It is why the first floating LNG facility will be moored on the Australian coast. I will show you after that. To mitigate the very high labor cost in Australia, so that the Shell decided to build this floating LNG facility directly in the Korea shipyard, which are very, let's say, have a strong reputation of cost control and delivery in time. So basically, as I'll tell you before, FLNG explanation is to mitigate cost escalation, to catch up offshore fields, obviously, and also to mitigate an early depletion risk. Basically, what we do if the field appear to not have the expected quantities. Now, few examples of floating LNG. Okay, so the one I mentioned, obviously the floating LNG is not moored close to Westminster Array. It's just for the sake of the understanding of the size of these facilities that I show you this picture. But it's a very important facility. Basically, here's the flare, which is always very impressive because the flare can be used to route a large amount of gas in case of shutdown of the facilities. On the top sides, we can see all the liquefaction stuff, and on the bottom of the vessel are located the tanks. So there is different approach. In the Shell approach, the shuttle will come alongside the Prelude FLNG. In the case of the Petronas project, they will normally come on the aft of the vessel. And there is also, let's say, low-cost solution. Golar is quite familiar with this creative solution, and you can, I guess, you can imagine what it consists in. It consists of an existing vessel completed with 2 liquefaction blocks, so that it saves the cost of building the initial vessel, and here you can see the flare. So different approach, but driven by the same philosophy, the flexibility that offers the floating LNG technology. Okay. Now, the LNG import terminal, we are talking about the regasification facility. You can see that this regasification facility are spread worldwide. And I will not enter into detail, but what you can see is that Japan is a very important importer of LNG, the first importer in the world. And this was even more true after the Fukushima disaster that led Japan to shut down all the nuclear power plants. And the second importer is South Korea. So it is not that, okay, here it is that it is. You can see it, but they are huge terminals, very, very, very massive terminals. Newcomer, China. China is importing more and more LNG and building new terminal very quickly, if either an offshore terminal or floating terminal. I will explain you the difference after that. And in Europe, there is, I guess, 25, 26 import terminal, but they are running at a very low rate. I will show you right now the figures. So as you can see, there is plenty of spare capacity in the regasification terminal. Basically, we consider that there is twice as much regasification capacity as liquefaction. Okay. Especially when a regasification terminal is used as a peak shaving facility, which is the case in South America, in Latin America, especially in Brazil, where the LNG is used for power purpose during the dry season, where hydropower is at a very low level. And basically the same in Argentina, but with lower impact of the hydropower. It is more a seasonality impact. If we go to Europe, you can see that the level of use of the terminal in Europe is very low. It's very, very low. This is clearly because competing market with Japan buying the LNG at higher prices, and Europe with a decreasing demand, so that Europe is preferably firstly using a gas pipeline coming from Russia or Norway. In Asia, the situation is a little bit different. You can see that the level of usage and also the quantity available are very important in Japan and Korea. Taiwan also is running at 100%. It's also a relevant importer. China is now coming on stream, and you can see that it is basically the only developer of regasification capacity with India. In the rest of the world, the tendency is very flat between 2014 and what it is expected in 2020. In terms of cost, I don't know if you remember the previous slide, but we were talking about dollars per ton of yearly capacity. So we're talking about 1,000, 2,000. Here we are talking about 10% of this cost. Basically, it is basically the message is that the regasification terminal is cheaper than the liquefaction one. For a conventional terminal, onshore terminal, we're talking about $200 per ton of yearly capacity. But this capex can drop down to $100 per ton in case of the use of floating solution. So what you can imagine is that what you win in terms of capex, you will lose it in terms of OPEX efficiency, fuel costs. So let me present you the solutions, the different solutions. So in terms of scales, I first obviously present our terminal, 300,000 cubic meter of storing capacity. We can go to very important terminal in Japan, 2.6 million. They are huge terminals, and with a ratio between send out and energy store, which are very different because of the long distance to reach the Japanese market. Okay, so that while in Spain, as an example, we can expect 8 days journey to deliver LNG to Spain. In Japan, it will be the double, so that it explains, let's say, that they intend to cover the possible problem within the supply chain by increasing the level of storage in their terminal. And to conclude this slide, an example of small-scale LNG. Jesus will go deeper on this topic, but the message here is that there is a full, let's say, flexibility in terms of sizing of the terminal, and that you can go from 500 to 2.7 million. Now let's have a look on the floating solution. Floating solution are let's say the new tendency, the new trend, and basically nowadays 50% of the new projects are delivered under the floating solution. So if we start from, let's say, the most onshore likely solution, we can talk about FSU, floating storage unit. So in this case, there is a vessel which is in charge of storing the LNG, and there is an onshore on board the platform, whatever the solution is employed, which is in charge of the regasification of the LNG, and after that the let's say regasified LNG is sent to the grid. Here we can see the shuttle vessel which is in charge of bringing the LNG, and we can have, let's say, a lighter solution. The lighter solution is this one. This is a conventional LNG carrier fitted with regasification equipments on the aft. Okay, so they are typically a shell tube exchanger using either seawater or a closed loop heated with boilers. Basically, the choice of a closed loop or seawater depends on regulation. In any cases, it is forbidden to use the seawater, so that they use the closed loop. Obviously, in terms of OPEX, it have an important impact because the closed loop is much more expensive than the open loop with seawater. So here, a floating storage regasification unit, FSRU, and here the vessel with a double jetty, where the both vessels are moored, let's say, on a conventional way. We can also see another solution. This photo is taken in Escobar LNG terminal in Argentina. And here there is just a single jetty, so that the FSRU, basically the same as this one, is moored on, let's say, on a standard way. And this small vessel, in this case a CF Polar, I guess, is moored alongside the FSRU. And here the transfer can be done basically with flexible hoses, but there is also example of, let's say, standard loading arms installed aboard the FSRU. And finally, let's say the lighter solution is directly buoy. A lot. Accelerated vessel in the aft part are fitted with this system, and so that they directly connect with flexible hoses and are in charge of sending the regasified LNG at the grid, and the other vessel is coming alongside. So these operations are much more, let's say, tricky, and they require the very safe place to be realized. Switching to the shipping. the first shipment of a commercial LNG carrier was in 64. 64, and the LNG was loaded in Algeria, Arzoum, so that here you have the illustration I showed you before in the quality table of LNG. You will see the quality of this LNG and the presence of EVNs because of the, let's say, less efficient coolant process, but it's a detail. And the first commercial shipment was from Arzoum to Canvey Island in UK. Aboard this vessel, the Methane Princess. The Methane Princess is quite a small vessel. When Jesus will tell you about the vessel, you will see that there is today a vessel up to 260,000 cubic meters. Basically, if we want to, let's say, to make the idea of an LNG vessel, there is three main, let's say, a definition to describe an LNG vessel. The technology of the tanks, the technology of the propulsion, and the size of the tanks. So, talking about the technology of the tanks, today, almost all the new builds are built on GTT, which is a French company, GTT technology. They are membrane tanks. The maximum pressure is lower than 700 millibar. So basically we can talk about atmospheric pressure, that it is because the LNG is subcooled at a minus 160 grades, so that it allows the vessel to operate at a very low pressure. And I will show you after that a short video about the insulation technology regarding this technology, because I guess it is the relevant one to talk about because it is the most employed worldwide. The second technology employed for conventional vessel, I'm talking about vessel in the range of 140,000 cubic meter of capacity, is spherical ones. And at the very beginning of the history of the shipment, we can observe also the construction of LNG vessel according to the prismatic technology, self-supporting. Let's say that it can be compared to the onshore tanks that are now built in Europe in terms of technology. So now, if we talk about small scale, sorry, before talking you about the different pros and cons of the different technology, these new tanks are coming cylindrical and below on the small scale vessels. Transportation of LNG on the small scale. We are talking about few thousands of LNG. It is a very interesting technology because of this ability to support higher pressure, so that in terms of management of a boil of gas, it is a strong strong pros, clearly, because it reduces the losses of gas during the shipment, during the journey. MOS versus GTT. The first consideration is sloshing. Sloshing is what happens when a tank is not full or empty. In the spherical tanks, there is absolutely no problem. You can imagine that if, for example, you are taking a bottle of water, you put it horizontally, you round it, you will see that basically there is no problem for the liquid because the form occupied by the liquid is the same. So the sloshing behavior of this technology is excellent, is very good. It is why they are sometimes used to be floating storage and regasification unit, because these vessels have to be able to work at any level of LNG inside the tank, logically. And for the GTT, it is not the same. It is not the same consideration. For the GTT tanks, there is what they call a forbidden zone, which starts from 25, 15 in many cases, up to 65%. In this range, the vessel is not in position to be in navigation, because of the risk of slushing of waves formed by the LNG that are strong enough to cause important damage to the tanks. Okay, so in terms of flexibility, clearly 1 point for the MOS technology. In terms of capacity, logically, by talking about a sphere, the beam is a direct consequence of the size of the tanks. So that basically what we are observing nowadays is that 260,000 cubic meter vessel like Kumax, we will tell you about Kumax after that, have the same beam of a 170,000 cubic meter MOS technology. Okay, so it is usually the advantage these days, especially when we are talking about crossing the Panama Canal, because the new locks of the Panama Canal will be open at the end of this year. And it will be very complicated for the MOS vessel to cross the Panama Canal because of the excessive beam. The beam will be limited at 45, 48 meters. Okay. In terms of thermal insulation, MOS are not that good as the membrane, and the membrane vessel where the insulation is higher. And in terms of pressure resistance, which is also very important, the MOS are better. You can imagine why. Sorry, you can imagine why, because the sphere has a better capacity to support an higher pressure. Okay, so in terms of ball of gas management, may I will give 1 point to the MOS technology. Okay, so we'll now show you a short video about the GTT technology. You can see that it is a kind of, let's say, Lego in terms of building, very interesting to see. Okay, so we were not able to comment the video when the video is played, but what you can see is what is quite surprising is that one of the main components of this technology, Mark III, is wood. The tanks are made of wood. It's very interesting because the capacity of the wood under the cold condition is excellent, and so wood is a preferred material just after the primary barrier. And now to finish with the vessel, I will tell you about the propulsion technology. So the first technology employed was basically the steam turbine system. The steam turbine system has an important advantage is that exactly as a boiler in a refinery, they are dual fuel boiler able to burn either heavy fuel or a boil of gas, because the natural evaporation of the LNG along the journey is burned directly for the propulsion of the vessel. So the LNG is a unique example of a vessel using its own cargo to ensure the propulsion of the vessel. Very interesting. The steam turbine system. So basically, it consists of burning gas or heavy fuel in a boiler to produce steam and to use steam through turbine to ensure the propulsion of the vessel. Now on the new build, it is not used anymore because of the, let's say, poor efficiency. The new technology is coming from a, let's say, a diesel electric system. So the idea is to use a diesel cycle motor when you burning gas or fuel or diesel oil, sorry. And this is used to produce electricity, and then the electricity is used through electrical motors that are ensuring the propulsion of the vessel. So in terms of, let's say, construction of the vessel, it's very interesting because there is power generation on one side and the propulsion on the other side. And there is the possibility to switch the generator, to switch the motor independently, so that it is very, very efficient system. So I was talking, sorry, about this one. One of the inconvenients of the problem of this system is that this system is very, let's say, strict in terms of quality of fuel regarding gas. So all the EVNs are returned to the tank so that after a long time of inactivity, it can impact negatively the quality of the cargo, of the LNG as a cargo. So it is important to notice. Another technology was built aboard the Qatar vessel. It was also diesel engine, but burning heavy fuel oil. After 5 years of operation, the Qatar fleet manager decided to convert the Kumax because it appears that it was much more interesting to burn gas than fuel. So this decision was made when the crude oil barrel was close to $100. I'm not sure that they will completely implement this strategy when seeing the new crude oil prices. And finally, there is also last technology, slow-speed dual-fuel diesel engines. So we are talking about two-stroke motor. So the major problem of the two-stroke motor are the pressure requirement. It requires the gas to be highly pressurized before entering into the motor, into the combustion chamber, so that it can in some way underpin the overall efficiency of this motor. Intrinsically, it is more efficient, but the energy wasted for the pressuring of the boil of gas is negatively impacting the efficiency. So that basically nowadays the two technologies are competing without a clear advantage of which one is better and which one is more efficient. Okay, so now I let the floor to Jesus that will give you a large overview of the LNG import facility.
Okay. Now with the nice explanation that we know more or less about LNG and how the LNG world and how this LNG supply and consumed by different actors. Now it takes the time to know how this comes to real life. And to make this real, at the end we have to build concrete nuts and structures. And these kind of facilities and infrastructures are what is the supply chain made of. I will start with the LNG terminal description and operation, and also focus on the LNG vessel navigation and studies that are necessary to confirm that a place located or a place selected to receive or to have an LNG facility is suitable for that. So in the previous part, Laurent talked about the first fleetment of LNG that was done in Algeria, and the terminal that was in the 64, I remember. Yeah. So now we are in the 2015. In the 1964, we were not born, so even we could not see that. So we are people from this century, not from the last century, we can call it like that. And the things has changed a little, but the essence is exactly the same, because the product, the LNG, is exactly the same. Different qualities, of course, but the technology has not moved very, very fast like in other technologies, like in the communications or mobile phones, that is like the prehistoric and the future in 10 years. We can see here the LNG terminal of Mugagos. We have two tanks. Each of them is 150,000 cubic meters storage capacity, and our production capacity, as Laurent said before, is 3.6 billion cubic meters of gas per year. Here we can see the actual biggest LNG ship. This is a Q-Max. It's 10 times bigger than the other ship. And what is important is that the efficiency situation is quite better, because with the same crew, practically the same crew, you can transport 10 times more cargo. I will try to give you some big numbers or rough numbers of values, costs of things, because Laurent was talking about the cost. We know that the liquefaction terminal is like 10 times more expensive than a regasification terminal. But I will try to give you big figures. The values will not be really precise, because they will depend a lot on the price, on the market, the demand of construction facilities, and of course the price of steel and different products that compound this terminal. So just for making you an idea, a liquefaction terminal may cost like $1 billion. This is $1,000 million, European 1,000 millions, to $2,000 million. And I don't know the number, maybe Laurent can help me. These Australian projects, they are going up to 40 billion or 50 billion with B. This is 50,000 million of dollars cost for building this kind of facility. So the investment is, we can call it, simply huge. For an LNG terminal like the LNG terminal of Mugagos or similar one, the investment could move from, we can say from 200 to 400 or 500 millions of euros, depending on the technology and the construction strategies that we follow. And for an LNG vessel like this one or a smaller one, we can talk about roughly like between 150 to 250 or 300 million dollars, something like that. Depends on the book orders that these shipyards have. Laurent explained that this big market is, we can say, like a big scale market with big vessels, with huge amounts of investment, huge amounts of tons and moving around the world. But now, comparing with the oil market, now everything is trying to move to the smaller scale, to the small users. And this is really related with these highways in the sea, because most of these LNG consumers will be the ships that will navigate in the world. Here we can see two typical, real and existing examples, small-scale ships. This is the Coral Methane and the Cryonet Knudsen. These two normally work in the Norwegian area and the Scandinavian area. And the sizes we can see is that they are 117 meters and 69-70 meters. As you can see here, the comparison of the size, this is a normal standard a bigger scale ship, which is like 80,000, 90,000 cubic meter capacity. And here, this small thing is the Cryonet Knudsen. It's only 1,000 cubic meters. And the Coral Methane is 7,500 cubic meters. So you can see that the initial escalation of sizes in ships now is changing to a de-escalation of sizes to use these all ships as suppliers. In this area, in Reganosa and also a lot of actually the LNG market, we are moving to analyze this market to try to improve all the logistics, and we are using our knowledge to be used in the design of a new ship. This is an example of the new ships that we are designing to the engineering company in Spain, that we think that will be the state of the art, because we are trying to make it as the best as possible with the best technology in terms of the three points that Laurent talked before about the containment, the propulsion, and the size. Because yes, and the navigation. Because this normally in Europe, if you look at internet, there are a lot of references. There is a lot of navigation for barges. Parts for river area in Holland and also in Germany. And when we are talking about Atlantic and ocean navigation, we have to build a very, very strong ship that can navigate from Europe to the United States, for example, or to Africa. And this is our approach for these kind of ships. It's like 8,000 to 9,000 cubic meters. And GTT, also a membrane storage that can transport this LNG either to consumers onshore or maybe to consumers floating like bunker fuel. I think also the previous teacher talked about bunker, so we will not enter in more detail. For the vessel sizes and also for the access to our LNG terminal, because the experience that we can share with you, we follow like a very step-by-step process, and making a lot of effort and a lot of analysis with the best institutes for simulation of LNG navigation, LNG and vessel navigation. So we started with the standard LNG ships of 120 to 100,000 cubic meters. That was the normal ships that were built and navigated in this year, in time when we started the LNG terminal. Here we can see the number of LNG vessels and the dates of construction. Yes, so we can see that over the time the capacity is increasing, and now if here it is very, very slow. Now the small capacity is also increasing. The construction of a small vessel, the ones that we saw before, is increasing. So after making different steps and a lot of hours of studies and simulations and sending all the pilots that we are working in the river of Rol to these simulation centers, we made all the safety procedures that will allow will allow our terminal to receive from the smallest to the biggest LNG vessel. The biggest, I mentioned it, is the Q-Max, a Qatar ship that can transport up to 266,000 cubic meters of LNG. The price of the cargo, of course, depends on the price of the LNG that is transported, that can be, with no big error, between $20 and $30 million per cargo. We are talking about a lot of money moving and sailing around the world, so it's very, very important to increase the capacity of these LNG vessels to transport the maximum money at the end and energy. Next slide will be a video that we will see, and as we cannot comment when the video is running, this you can find it also in YouTube. It's an open video. You have the reference there. So you can see here a ship called Barcelona Knutsen sailing into the Rio of Ferrol. You will see the first part of the video are the pilots. The pilots are people, captains, professional people that take care of the ship and go on the bridge together with the captain of the vessel, and will guide the captain and the crew to pass through special areas, narrow areas, or port areas. In all the ports have two or one pilot on board normally when they approach. You can see also that in the first part of the video, when they are approaching to the ship, they are climbing literally to the vessel, and they will put a very big yellow luggage. This yellow luggage is a navigation system that we share with the pilots that help them to know the route of the LNG vessel and know exactly the speed and how the LNG vessel will sail with some time in advance. So this makes the navigation more safe. At the end of the video, you will see how the LNG vessel enters the river, and you will see also how the LNG vessel is rotated. Is a shuttle to approach our harbor. You will see that the strategy, we can call it like that they use is to rotate 180 degrees to put the bow to the external part of the port, and also they approach parallel to the port. Normally in other ports, like in Japan ports, they use a different approach that they hit one of the fenders, and then from this point they rotate. But here in our port, and mostly in Spain, the strategy is to move absolutely parallel to the port, the jet, the area, to the fenders. So this will minimize the impact of the fenders and will reduce also potential damage to the ship. These LNG ships, you'll see that they are huge vessels. This, for example, vessel is 293 or 94 meters length. It weighs like 150 or even more, 150,000 tons. There's a lot of mass moving. So it's very, very important to control the speed, the approach of this LNG vessel. For that, they use this GPS system, and also in our terminal, we have a laser sensors that give the pilots with a special device the speed and the angle and the tendency, if they are accelerating or decelerating, to contact with the less pressure and less speed to. So we will see now the video, and after maybe I can comment a little bit. Mm-hmm. Okay, we are back. What you have seen is really 1 hour navigation time. So it's accelerated, and there are some cuts in the navigation, but it really takes like 1 hour or 1.5 hours. And when this how you can say rebound, or this effect at the end, that seems that the ship is shattered, is like shaken, like a small nut navigating in the sea. In the real life, you cannot see it because the vessel is so big and the speed is so low that it's not really appreciated. You cannot appreciate that because the approach is like the speed of speed that these vessels use is like 10 centimeters per second, just to minimize the reaction force of defenders to the ship. In the next video that we will see, the next video is more or less the same, but what the pilots see on the bridge, we're using this GPS advanced system that we provided them, and also that the ship has. There you can see both images, the navigation on the chart and the real video is the same video that we saw before, but we can see from the top. And it's really interesting how these small things, these red things, are the tacks that normally help the LNG vessel to maneuver. In our case, we use 4 tacks, 2 at the bow, 2 at the stern, always helping the ship. Also, in the right side, you will see the speed in different areas of the navigation. You will see them in the channel approach, and also when they're approaching to the key here in this image. What is important in terms of navigation and control of the ship is that there is a water flow around the rudder, because if there is water flow, there is enough tons of water navigating in the rudder, then the rudder, when it turns, it will make the moment and the effect to turn the ship correctly. So that's why this vessel will navigate up to 5 to 6 knots. And these small tacks, the tacks on the bow, on the stern, are used like kites, like the kite surfing, more or less. So they are using their physical resistance to advance to break the LNG ship. This is strategy we discovered and we tested in the simulation centers, and we applied it not only for the LNG vessel but also for all the ships that enter in the river of Ferrol and in other ports. They are also using, because it's quite more effective than reducing the speed of the ship. So we will see the same video again. It's like 1.5 hours, but the speed up, and you will see in the final stage, this image, how the LNG vessel is turned, how it approach to the key, and how it is brake, because it's brake, how he moved backwards, and then she approached to the key. We will see now the video.
Actividad tiene que volver a aparecer. Sí.
So we have seen more or less the same maneuver, but in how the pilot sees in the bridge. So it's really interesting how these tags help the ship, and it's very important to define the capacity of these of tags to help the ship when she needs it. Maybe sometimes they pull, sometimes they push. So is the pilot that is here in the bridge who is always speaking with these tags to find the best support and the best help for them to enter the ship. Here we can see a normal or a standard LNG terminal process, and maybe we can speak together just to make it more more clear. What is important is to define two things. It's a pure physical process, and there are two main differences in pressure and in temperature. We have the side of the vessel that is a low temperature, is minus 160 degrees, and low pressure. It's like ambient pressure. We can say like 150, 160 millibar gauge relative to ambient pressure. And also we have the LNG tanks. That is more or less the same pressure and the same temperature. A little bit higher, the working pressure. We can work up to 290 millibar gauge. In LNG terminals, we speak normally with gauge reference to the pressure, because we work below ambient pressure or over ambient pressure. We can also work with vacuum. So the process starts with the transfer of the LNG to the tanks. It's always the LNG who pumps the LNG to the tanks, and the speed or the flow is, in our case, is 12,000 cubic meters per hour using 3 LNG liquid arms located in the key area. When the LNG tank on shore is getting filled, then there is a vapor that is increasing the pressure in the LNG tank. So this LNG, this boil of gas, the gas generated by the increase of the temperature of the LNG, is sent to the vessel, because the vessel is happening opposite. Is the level of the tanks is being reduced, and there is an empty space that she needs to fill. And that's why the vapor that we don't want in some way, we give to her because she needs this boil of gas. So we do all these transfers of the cargo of an LNG vessel between 12 to 18 hours, depending on the pumping capacity of the LNG vessel. And the total time the LNG vessel is moored on site is, we can say, is between 18 to 24 or 30 hours, depending on the ship. Now, Laurent will explain what happens after the LNG tanks.
Okay, so additionally to the displacement of LNG, which is responsible for the, let's say, the transfer movement of boil of gas, the back movement, there is a natural evaporation of the LNG stored into the LNG tank. Okay, so to avoid pressure escalation, Jesus told us right now that the maximum allowable pressure inside the tank is 280 millibar gauges. This pressure is managed by boil of gas compressor, and we are proceeding to reliquation, recondensation of the boil of gas. So why? How do we do that? Inside the tank, submerged into the tank, are the LP pumps, the low pressure pumps. The LP pumps are pumping the LNG from the tank at let's say 200x millibar, and there is from, let's say, 40 meters of liquid in maximum scenario down to 10 meters, 6 meters of minimum 8 of liquid, and the liquid is pumped till, let's say, 8 to 9 bar gauge. Okay, so the LNG is pumped. Here the LNG is available at 8 bars, so it is a perfect pressure to proceed to truck loading. So the truck loading station is using this LNG. Let's say it is quite let's say a marginal flow, because the pump are able to give 440 cubic meter per hour, and the truck loading facility is requiring 60 cubic meter per hour, basically 1 hour to fill a truck. So at this stage, the LNG is still at minus 160 degrees, but 10 bars, so that the LNG is subcooled. So as a subcooled fluid, the LNG is in position to receive the gas coming from the tanks. The gas is coming at a temperature, here we are at typically a minus 80 degrees, but due to the compression, the temperature can increase to 0 degrees and even more. We observed in the past up to 80 degrees. But because of the subcooled LNG, there is a recondensation of the LNG. So obviously, what you can imagine is that the problem is coming when there is no send out. When the terminal is not working, it is like a bicycle, and we have to put a foot on Earth, basically, because if there is no LNG here, there is no more capacity to recondensate the ball of gas. So what happened in this case? We use a flare. So here is the flare. We call it a combustor because of the Mugardo specific, let's say, building of this flare. In Mugardo, there is no pilots. There is no permanent gas burn into the combustor. So this is a combustor, also called a ground flare. Okay, and as you can see, the location in the process of this combustor is not, let's say, an hazard. It is not random. Sorry, it is in a position to be dedicated to the vessel for the post-dry dock operation that require to let's say, to put the vessel in operation so that we can here close the valve and dedicate the ground flare for the vessel. After the recondenser, we are 8 bar, 9 bar, as I told you before. We are proceeding to the second stage of pumping with high pressure pump. Here are 2 stages pumps, and here are 11 stages. So we are pumping from 10 bar to 100 bar, okay, to 100 bar through these pumps. As you can see, the flow is a little bit lower than the primary pump, basically because part of the LNG is routed through the trucks. And after that, we have basically 2 ways of vaporizing the LNG. The LNG is now at minus 160 bars. There is no thermal exchange at this stage. And the pressure is 100 bars. So we are above the critical points of the LNG. So we are making a vaporization at critical stage, either by using seawater. Okay, so we are pumping much more seawater than LNG. Basically, the basic rules, let's say, the inch rule is 10 times, so that when the LNG is vaporizing from minus 160 to 0 degree at the outlet of the vaporizer, the seawater is only cooling down by 6 degrees. It is an environmental regulation. We are not allowed to cool down the seawater by more than 6 degrees. And the alternative, which is not the preferred one, because as I told you, for the FSLU technology, it requires to burn your own gas. We are able to vaporize the LNG within an exchanger, which is basically an exchanger submerged within a pool of water, and this water is hit by a burner where we burn the gas. Okay, so it is less efficient because you have to burn your own gas, but it is a backup system, especially when you have to work for maintenance work on the seawater system. After that, the gas is at the grid pressure, which can be up to 82 bars. It is metered, which is very, very important because Jesus insisted before on the high value of this raw material. So it is metered and authorized, which is not, let's say, a common practice. It is not the case in all Europe, but in Spain it is mandatory. The idea is to be in position to detect a leak because of the special, let's say, smell of the gas leak. Okay, and then it is sent to the gas pipeline.
Okay, so as this class is based, or it's focused to the LNG chain, and the supply from the terminal to the truck, we will focus on the LNG activity and how the LNG unloads, the LNG vessel unloads the cargo, where the cargo is stored in the LNG tanks, and how this cargo is shipped to the. It also, we will see how the cargo can be loaded back to any ship independently on the site. In here, we can see, it's an interesting trend that we can see in this gray color that how the production or the consumption of energy in Spain has increased from this year 2008 2014.
Total gas demand, yeah?
Total gas demand, sorry. But we also can see here in blue, light blue, this is the regasification capacity of Reganos that is following the gas demand in Spain. But here we can see in dark blue, the LNG entered the terminal. So there is like a discrepancy why this regasification capacity is increasing, but the LNG load is increasing. And more or less we can see that the vessels, number of vessels, more or less gets flat. And what happens with it? Laurent talked before about this global prices difference, the Asia price, the Japan price, and the problem, and how the global trade companies try to solve that. How the European business of the European area is managed with a long-term contract of supply of gas. This, as we could see that these investments of thousands of millions of euros or dollars means and requires long-term agreements. So normally the producers used to sign long-term, by long-term we say 20-25 year contracts with users to buy this LNG. There are different types of contracts depending on the approach that the clients want to do, but some of them are take or pay. So if you don't take the LNG in the production place, you have to pay it independently if you use it or not. So when there is a very big gap in price between the European price and the Asia price or the South American price, this reloading takes sense. And Spain, we could see previously that the gas demand was really decreasing as well as the European, but the Spanish was really hard, the decrease. How the trading companies saw that the opportunity and used the opportunity to reload the LNG that they must unload in Spain to other countries. This is the reloading service. In Reganosa, we were not the first, because the first was another company, but since 2010, we did it in a very organized and controlled way, and we didn't have to modify too much our facilities because they were designed to do this since the first moment. And we increased the number of cargoes and the number of energy and reloaded to these places working differently in the world. And for example, from our terminal in Spain, we have sent LNG to Asia, to America, or even to the Middle East. Also, Laurent spoke before that the post-drop services and how our terminal is designed allows us to give a special service to the shipyards that we have just in front of us. This is like an image of the river of Ferrol. We are here located in the south part of the river. So we are just in front of a very important shipyard specialized in repairing LNG vessels called Navantia. Navantia, depending on the year, is in the top 5. The top 3, top 5 shipyards competing with the Asia shipyards for repairing vessels. They can repair up to 25, 30 LNG vessels per year, something. So what is the ideal flow for an LNG vessel? So when the LNG vessel is used by the trader to transport the LNG, she may come to our terminal and she will unload all the LNG. After unloading all the LNG completely, emptying the tank, regasifying the tanks to make it safe for workers of the shipyard, the LNG vessel can go to the, this is what?
Hill out.
Yes, what is called exactly. What is the heel out? Heel out means that she takes out all the heel. The heel is the small part that is remaining in the bottom of the LNG tank, and she takes out of take off all this gas and then goes to the shipyard. In the shipyard, the vessel is repaired. They do whatever they need, but they have to heat up the tanks. They cannot enter in the tanks at minus 160 or minus 100 degrees. So when the workers need to enter in the tanks, they have to heat it up, to put it in ambient temperature, and also to put in with oxygen. And oxygen and gas, they are not very good friends. So they have to do a complete degasifying of the process, an inertizing of the process, and then they can start. When they finish the work, the LNG vessel and the tanks of the LNG vessel are full of air, normal air, and at ambient temperature. So this condition is not compatible to receive LNG. So the LNG vessel should come to our terminal, and we will do several things. We can first inertize, maybe in the shipyard or maybe in our terminal. Normally it's more efficient to do it at the shipyard, but then the ship will arrive to our terminal inert. If not, we will do it. Then we have to gassing up, so we take out the inert gas and we put gas at ambient temperature. We can say like that, and then we do what is called the cool down. That is, with a small flow, we can little by little cool down the temperature of the ambient to minus 140, minus 150 degrees. And when the LNG tank is full, then we can reload completely the LNG that the ship needs. We and other terminals, we can reload completely the vessel, so fill all the tanks, or maybe we only fill one tank of the 5 or 4 tanks that normally these vessels have. And then in the navigation route back to the destination where the vessel will be reloaded or loaded completely, the vessel will do the same process but with their own resources. So they will use a small amount of LNG that we have put it on one tank to gassing up and then cool down the rest of the LNG that she has. So this process can be maybe partially, maybe the LNG vessel has not come to us to unload and she has gone directly to the shipyard, but she wants to leave back to the destination completely loaded. There are a lot of combinations, but at the end we have done up to 30 operations since the year 2011. So making this a good opportunity for our terminal and also for the Navantia shipyard. That is a really unique location for this kind of service. In the next slide, we can see the second way that we can send LNG. This is by truck. Why by truck? Normally, when there is no infrastructure related with gas pipelines in isolated areas in our region, in Galicia, is an example, then the users, the people in the houses or the industries will not have access to this LNG or to the gas. So to avoid this delay or to reduce the time when they could access this gas, there is another option to use what is called satellite plants. Satellite plants is a small tank going from 10 to 200 or 400, depends on the demand, LNG liquid that is installed in the vicinity of the consumer point, and LNG is supplied by truck. These satellite plants, we also saw it in the presentation that Ran did in Denmark, for example. So, for example, in ports where the LNG will be used as bunker and there is no infrastructure yet to supply in a big scale mode, these small satellite plants, in the case of Denmark, was 500 cubic meters, are supplied normally by trucks. So, in our terminal in 2014, we load up to nearly 10,000 trucks.
Sorry, just to comment you that there is a mistake, an inversion. So on the right axis, you will read the energy loaded in gigawatt hour, and on the left axis, you will read the number of operations.
Yes. Sorry for that. So in general terms, these 10,000 trucks are loaded were loaded in our terminal, and more trucks the whole Europe. Spain is the leader in truck loading, and in 2014, up to 36,000 trucks were loaded in Spain. And we load in our small terminal more trucks than in the rest. So this is a demand that is increasing continuously, and in the future will also increase for supply the LNG as in those places where there is no strong infrastructure. In Reganosa, we also have seen that these sea highways and sea routes of navigation in the world are increasing, are also now limited with environmental restrictions, environmental control areas. So, for example, in the north of Europe, there is a very high restriction in SO2 and NOx emissions and CO2 also emissions. And from the different options that the owners of the ship have, depending on installing scrubbers or changing the fuel, most of them for new constructions, they are going to the LNG. And for this, we in Spain and in Europe, we put out like the global map, 2D dimensions. We can see that we are located, or Europe is located in the Atlantic area, of course, and here in this route of the Atlantic that receives all the vessels from Asia, South Africa, America, means that up to 40,000 vessels navigate every year route. So it's a good opportunity to have to have access to these routes to supply LNG. How? These small vessels that we saw in previous slides. So, and what is the most representative user? It's we have done several studies, and 21.3% of the order books of LNG powered vessels, these are vessels that will be powered LNG, are container vessels, medium container vessels. The medium or the mean or the expected capacity of the LNG tanks for these container vessels is between 5,000 to 6,000 cubic meters of LNG. That means that a total of 150 trucks will be needed to supply the LNG to these vessels. This is not practical because at the end to supply, only to load these 150 trucks will mean 150 hours plus the growth time plus the unloading time, that is more or less the same. So we are talking about 400 or 500 hours to make a normal bunker operation. So this is the reason that truck is feasible when the amount of energy is small and when it's just a spot supply. If you want to make a regular base supply, then you have to move to this small scale vessel. And it is expected, with according to some DNV studies, that in the year 2030, the 31.9% of the container vessels of the world will move with it. It's a good approach, and it's expected that all actors of the LNG supply chain want to take advantage. Now we go in a very detailed, not very big detail because we are running out of time, on the main equipment. So the main equipment used to unload or reload the LNG are the unloading arms. When the scale or the size of the ships is small, instead of using these huge unloading arms, they weigh like 90 tons, the height is like 40 meters, and each cost like $500,000, something like that. We can move to hoses, to flexible hoses. What is important for an LNG arm, unloading arm, is that what is the compatibility. We can see here in this gray area, the compatibility area, the movements of the LNG arm against the vessel. Here we can see the box, these two boxes are the manifolds of the vessels. And of course, when the LNG is very, very small, is a very small LNG vessel, this arm will not reach the manifold of the vessel, because these arms are designed not only in our terminal, in all the terminals, but we can say bigger scale arms. Here we can see two limit lines. This a pre-alarm line, that means that if the ship is moving out of keys by any reason, by the wind, by the tide or whatever, this alarm will generate a close order of the valves that the arm has. And also the two motor alarms, the ESD1 and the ESD2, that is emergency shutdown. One that is closing the valves and the pumps of the ship, and the ESD2 means that the another valve is closing, there is a physical disconnection of the arm, and the ship can move out of the terminal without any leakage of.
Yeah, absolutely. So what I want to add to the Jesus' comment is it is important to notice that it is especially challenging the design of the loading arms in the Atlantic coast because of the tides. So additionally to the natural movements of the vessel, that it is getting empty, through the unloading operation, you have to add the movement of the tide, which can be up to 4 meters amplitude in our region.
Yes, and in some other regions, like in Canada or in some France regions, it could be up to 10 meters. In some German areas, also 8 meters. So these are very, very flexible structures that moves following the ship. In the next video, we can see here that the capacity that is each arm is 4,000 cubic meters, so 3 arms makes this 12,000 cubic meters per hour of capacity, and they normally work at the discharge pressure of the pumps, like 4, 5, 6 bar, depending on the ship, but the design pressure and the maximum pressure is quite big, quite high. Here we will see a video of a manufacturer, one of the main manufacturers, company called FMC, but it's very, very interesting, this video, because we will see how this part of the activity simulates the movements of the ship. Also, and this part is the arm. You will see that this arm is white, and it's not painted, it's the ice, because this arm, for making this test, is full of liquid nitrogen. It is really also cold, because they have to simulate first the movements with cold condition, plus the liquid weight inside the pipes, because these are rigid pipes. These are rigid pipes, and they are connected with silver joints that allows this movement. So here in this photo, we made a screenshot. You will see this small cloud that is this the amount of liquid nitrogen that is trapped between these two ball valves that we will see in the video that are closing when there is an emergency disconnection. When these two valves, when they close, the ball, the fair, remains a small space between these two balls, and when they open and they disconnect, the amount of the volume that is trapped between these two balls is liberated. So we will see the video now. So we could see how the LNG arm is moving following the ship, and how the valves that make this isolation, these ball valves, are closed when the arm reaches some distance, that it can be programmed by the terminal. When this happens, this of course is a test in a factory. This is done to check that the arm moves. And there is a special video on YouTube. Again, this video is available on YouTube, so you can download it. Here is the reference. There is a special video of a real unloading operation with a Nigerian ship. We know that it's Nigerian because of the color of the tanks, where we can see a full unloading operation with this 12,000 or 14,000 or 10,000, we don't know exactly the flow for this ship, when by any reason, by an error of the operator or an error of the system, lead to a disconnection of the arms. So you can see here, or you will see how the arm is frozen. This is ice. You will see like small drops of ice that fall from the ship, and also this cloud is the LNG that is trapped between these two valves, and when it disconnects, it's liberated.
You will see that there is 3 liquid arms and 1 vapor arm. So logically, the vapor arm are less weight, and it is the first one disconnecting.
Okay, so we will see this video. So back again. Oh, sorry. So you could see how the arms, this is the liquid, and the first one that Laurent mentioned was the vapor arm. They disconnect. We don't know exactly the reason for this, but in 10 seconds, everything is disconnected, and the arms were little by little moving back to the park position, as we could see in the demonstration video of the manufacturers. I think these arms are the same manufacturer as we could see in the video because of this structure. There is also another big manufacturer of Germany, is SVT, that is a different design, but at the end, the essence is exactly the same. Now we go to the LNG tank. The LNG tank is one of the most important pieces of the energy facility, and also it's Laurent mentioned before that the US facilities is a big investment that you can save if you want to transfer a receiving terminal to an export terminal. Here, this LNG is a typical one. The liquid is stored in liquid phase in the LNG at -160 degrees, and how this temperature is maintained cold by isolation. This isolation or insulation, insulation is made basically with perlite and foam glass in the bottom. Here we can see that this is a full containment tank. What means this? That in case there is a leakage or rupture in this inner vessel, the liquid will fall down in this perlite area, but will be contained by the concrete structure. While full containment, because the structure is on the bottom, in the wall, and also in the roof, the dome. Here, this cover is what is called a suspended deck, like a cover of the LNG to minimize ingress, and the space between the inner tank and the outer tank is normally like between 800 to 1 meter distance thickness, and this is full of perlite that is compacted. Here we can see, and also in the next slide we will see better, is there is some coils. And why these coils? This LNG is at -160 degrees. All the ambient is normal temperature, like 40 degrees, 20 degrees, whatever temperature. And the ground normally is at temperature of the air, like 10 degrees, 16 degrees. If we leave the LNG here, the insulation is not perfect, so at the end everything will be cooled down, everything, absolutely. And if we decrease here the temperature of the ground below, we put it below 0 degrees, all the humidity, the water that is in the ground will create ice. So you know that if you put a bottle of ice in your fridge, then the volume will increase. So it will happen the same in the ground.
The bottle will explode.
Yeah, the bottle will break, and at the end the ground will break. The stone can break. It's a traditional way to break the stones in the ancient areas. To use water and use the ice to break the stones. So these coils are used to heat, to maintain this foundation of the tanks at 4 degrees normally. It's a cycle, so it's a heating up, heating off, this on-off cycle to maintain this temperature always at the same value, like this point.
Electrical heating.
Yes, these are electrical heaters. There is another option for some terminals, for example, in Greece and also in Zeebrugge in Belgium, that this, instead of having this foundation directly supported in the ground, we can use piles to support the LNG tank, and there is air directly between the foundation and the ground. So this air is making this. Here we can see quite a nice description of the different layers of the tank. Is like a big thermal of coffee, and you have the energy at minus 160 degrees, minus 158, depends on the energy, and 1.5 meters far you are at ambient temperature. This is a scale more or less of a person. So to get this this complete insulation, there is some layers of insulation. Again, and the wood is used, now it's moved for other products like foam glass or cellular glass or different products, but it's like like a Lego of different layers of insulation and different products to avoid that the heat enters in the tank and the cold goes out of it. What is important in terms of construction is this inner tank. Inner tank has to be what is called the primary tank wall, and also the bottom needs to resist the temperature. If you put carbon steel, normal carbon steel for any structure, in contact with something below 30 degrees, by the proper structure of the carbon, it will be fragile, it will break. So if we are working with minus 160 degrees, the problem is higher. So to get out of this problem, basically also in the experience and some technology improvements, it was discovered some time ago in the 60s, 70s, that adding nickel to this carbon steel, the resilience of the carbon steel is improved. So by adding a 9% of nickel to these carbon steel plates, this carbon steel can resist this low temperature. The problem is that nickel is really expensive. If we are talking about in the London Metal Exchange market, that is the reference, the world reference for prices of metals, the carbon steel could be like between 100 to 200 tons per year, dollars per ton, to 100 to 200 dollars per ton, and nickel can move depending on the demand. That is like crazy demand, between $2,000 to $50,000 per ton. So in terms of volume of product, carbon steel, nickel, we are talking about 91 and 9%. But in terms of cost, we can be absolutely opposite. We can be like 80% of the cost of the plate is nickel, and the rest is carbon steel, depending on the demand. So the thickness of the wall and the different layers depends on the manufacturers and the technologies. In normal practice, in onshore, normally the membrane tanks, Laurent explained before, are not used because they are really difficult to manufacture, and it's not possible to decommission the LNG tank as easy as a ship. Normally a ship every 5 years goes to the shipyard and there is a complete review of the tanks. But for these onshore tanks, there is a 50-year time period of life of the tank. So normally there is no decommission of this tank, so it's really impossible to make an inspection. That's why the membrane technology is not really used and not suitable, and this carbon steel with 9% still is more preferred or more used in the market. Now we will see the last video, and here is the construction sequence of the LNG tanks of Reganosa. here what you see is the dome, the roof of the tank that is built on the ground of the tank. These tanks are made of, this is the exterior part of concrete. It's like a 40-meter high concrete wall. It's 850 millimeters width. And this dome, this structure is made of carbon steel because it is not in contact with cold temperature, with LNG, because there is insulation this part and the LNG, and is like a 72 meters diameter, is the dimension, and the weight is like 900 tons. So how these 900 tons are lifted 40 meters in 2 hours is very simple. We use a crane, but the question is there is no crane that can lift this roof. So a most simple solution was found, that is use the air, just a question of pressure and force. So at the end you have a very big surface, so you have a very big area where with a small force you can have a big pressure. And in the other way, there is we will see in the video like 2 or 3 blowers that are colored in blue that will put the air in a small hole. That so by the relation of the surface of the areas where the air is put in the tank and where the air has to go out of the tank, there is no option to go out because it's the dome. So it has to, at the end, the air is filling the tank and lifting the dome. This is the solution that is mostly used everywhere in the world to make this construction activity that is really impressive. It is the most impressive construction operation in these terminals. Here you can see these white things. All these things is the inspection of these weldings. All these weldings on these tanks are 100% X-ray or made or visual inspection or particle inspection, because once you finish the tank, there is no chance to make any further investigation. So we will finish. So we are back again. So it's really impressive how these 900 tons or 700 tons, depending on the tank, are lifted only with air. So it's really an engineering challenge to do this, but based in pure physics, the most ancient physics in the world. So at the end, the technology, when it works, you should not move it and you should not change it. And the final way to transport LNG, and the way that's what we normally use, is these truck loading stations. In our terminal, we have 2. In other terminals, have 3, 1, 5, depends on the demand. And this is a typical LNG truck. The vessel, the truck itself, the container is a vacuum insulated container, so it can resist or can have the LNG stored inside for more than 20 days without any overpressure. And it's a 56 capacity volumetric. It's a 56 cubic meters volumetric capacity. But for safety reasons, we only fill it up to the 85%. This is a typical manifold that is located here in this area, where the connections for the LNG hoses are located. Here we can see the truck loading stations with 2 trucks, and what is really important when you are transferring LNG or any flammable product is the earthing cable. No transfer of LNG in a truck can be started if there is no connection between the terminal and the truck to avoid difference in voltage, in potential. These are the 2 arms that we use to load the LNG truck. It's similar to the LNG vessel, but in a small scale. Here is the LNG arm, liquid arm, that is a 3-4 inch arm that can transfer up to 100 cubic meters per hour. We limit it to 60 to 75 cubic meters per hour transference of LNG, compared with the 4,000 cubic meters per hour of the LNG vessel. And this one is the 2-inch and 3-inch vapor return arm that receives all the boil of gas generated during the unloading operation and by the displacement of the LNG when we fill the LNG truck, is similar to the LNG unloading arm of the vessel. But compared with these 4 and 2 arms, for this truck, for the LNG vessel, is 16 inches. And here the operation is normally governed and supervised by the truck driver and the truck responsible and our operator. That normally they have to use special clothes to avoid any spillage or damage generated by drops. And in Spain and in other markets, all the transportation of gas by road is governed by the ADR, that is the European rule to transport flammable or dangerous goods. And all around this IDR, there are pure technical and commercial trading, what is the SLITR, that in Spain the access to the system by third parties, let's translate it like that, where the trading, the end users and the transportation companies or loading companies, we share the amount of energy that we have to load, consume or transfer. And also there is a commercial and pure trading part that is out of the technical logistics that is normally linking the energy trading company who sells the gas with the client who needs the gas and the LNG. And between these two is the transportation company that is hired by this or by this, depends on the contract, to transport the LNG that we load to these people. So you can see that it's like a wheel that needs to be very, very, very well greased to have all the energy where the energy is needed. And with this slide, we finalize our presentation, and we hope that it has been interesting for you. And of course, if you have any questions, we are